The Pacific Northwest, a place of unrivaled beauty and rich in natural resources, as well as home to over 12 million people, is a place defined by its landscape. This landscape is constantly changing. Humans have made their mark. Rivers carve through much of the Northwest. But truly, the most dramatic shapers of our landscape are geological in nature.
In the summer of 2011, we invited 2 community college students to participate in a cruise aboard the research vessel Wakoma as part of the National Science Foundation research project called the Cascadia Initiative. This was the inaugural activity of the Community College at Sea program, part of the broader impacts of the Cascadia Initiative, and built upon the larger University of Oregon undergraduate catalytic outreach or research experience summer and academic year activities. These CC at Sea students participated in a groundbreaking geophysical experiment offshore of the Pacific Northwest designed to improve our understanding of the region's most important and potentially hazardous geologic feature, the Cascadia subduction zone.
Hi, I'm Michelle from Umpqua Community College.
And I'm Eric from Mount Hood Community College. We were lucky enough to be selected through the UCOR and CC at Sea programs to go out on the research vessel Wakoma as part of the Cascade Initiative.
Essentially, we were given 2 tasks: to assist the scientific mission in any way we could, and to make a film about doing research at sea.
The second part is what you're watching right now.
In order to understand what we were doing on the ocean, you're going to need a little background information about the way the Earth moves and its effects on the world around us.
In order to understand why the Cascadia Initiative was created, it is necessary to understand a little bit about the world's geological processes. Our planet's surface, or crust, is broken up into many sections called plates. They move slowly, in some places moving apart, like the Mid-Atlantic Ridge, in others pushing against each other, which is what's happening off of our own Pacific Northwest coast. Where 2 plates meet, there is a massive slow-motion collision that takes place. Scientists call this a convergent plate boundary. When 2 continental plates collide, like India and Asia, you get huge mountain ranges like the Himalayas. When oceanic crust meets continental crust, the more dense oceanic crust subducts, or gets pushed under the lighter continental crust. Off of the Pacific Northwest coastline, we have a subduction zone that runs from Vancouver Island in southern British Columbia south to northern California. It was named the Cascadia Subduction Zone after the Cascade Mountains it created.
As the plate, the oceanic plate, is subducting underneath the North American continent, it carries with it, when it was on the seafloor, water circulated in cracks in the crust and got bound up in alteration minerals, so you had minerals that contain water, and sediments on top. And so that when that oceanic plate goes down into the mantle, when it gets to a certain depth, that those minerals with the water in them break down, and that water is released from the plate that's going down. And as that water then moves up into the mantle above it, it will cause that mantle to melt. And so once that water is put into the mantle, it actually acts like an impurity and starts making it melt when normally it wouldn't be melting. And so it's that, it's called flux melting, and that those melts then float up and come up at like the Three Sisters and Mount Hood and so on.
In addition to producing volcanoes, subduction zones can also produce some of the Earth's largest earthquakes. Two gargantuan blocks of land do not pass by each other easily, or peacefully. As the plates try to slide by each other, they get stuck in what are called locked zones. When enough pressure has built up between the two plates pushing against each other, they will eventually have what scientists call catastrophic failure. In other words, a massive earthquake is created.
Because the subduction zone is locked, the ground is going like this as the plates press towards each other. And then during a large Sumatran earthquake, it will slip like this.
With all of this in mind, Michelle and I set forth to find out what the Cascadia Initiative was all about.
We interviewed Doug Toomey, who's the principal investigator for this 4-year experiment, and asked him why we were going to sea.
Okay, so the Cascadia Initiative is really one of the first community experiments for oceanographic and earth scientists. And its goal is to take a look at the subduction zone processes as well as the formation of the Juan de Fuca plate, the hydration of the plate, how the plate moves beneath the North American continent, and how it gives rise to the interesting tectonic and volcanic features we see here in the Pacific Northwest. It also has many science questions, but in addition it has some significant relevance to society because it's meant to take a look at earthquakes in Cascadia. It's now recognized by the community that Cascadia is capable of rather large earthquakes, similar to the ones that have recently occurred in Japan and Sumatra. And so the effort here is to try and get a better idea of the structure and deformation throughout the arc so that we can understand how it's working a bit better and perhaps mitigate some of the hazards that are associated with it.
As you can see, the Cascadia Initiative is a huge project. It's funded by a $10 million grant from the approximately $800 billion American Recovery and Reinvestment Act of 2009. The ocean-based arm of this massive project is led by scientists from 7 institutions, focusing on developing, deploying, and gathering information from 60 ocean bottom seismometers, which will each spend 4 one-year stints on the ocean floor.
One of the things these seismometers will monitor and record is the newly discovered phenomenon of episodic tremor and slip, or ETS.
Before we left home, we went to interview David Schmidt to find out more.
In a traditional earthquake, we experience shaking on the Earth's surface, and that's caused by a very rapid movement on a fault in the Earth. And that rapid movement creates elastic waves that move the Earth and shake the surface. In the past decade, we've discovered this other class of events, which we call slow earthquakes or episodic slow events. People use different terms. And they're the same process where there's movement on a fault in the Earth. But instead of it happening really fast, it happens really slowly. And because it happens, and by slow I mean it happens over days, or months, or years. In a normal or traditional earthquake, that rupture happens in seconds. So we're talking about huge differences in time that this happens in. So on the slow events, they're so slow that you do not generate elastic waves in the Earth, and therefore you don't feel them on the surface. But they can be just as big or have just as much energy involved in a slow earthquake as a traditional earthquake.
Armed with a pretty good idea of what we were going to do and eager to get out on the water, we left Eugene and headed for the OSU College of Ocean and Atmospheric Sciences Ship Operations Facility at the Hatfield Marine Science Center in Newport, Oregon. We found the Wacoma waiting for us at the docks.
The Wacoma is a 185-foot dedicated research vessel owned by the National Science Foundation and operated by the College of Oceanic and Atmospheric Sciences at OSU. And then we're heading out on Wacoma.
Yeah.
Go drop some seismometers off on the Juan de Fuca plate. In addition to finding the ship waiting at the dock, we also found unfinished and half-painted OBS cages waiting for us.
Here's Andrew Barclay, a research scientist at Lamont Doherty Earth Observatory, explaining a little bit about what an OBS is. So you're the manager behind the creation of all these OBSs we've just deployed here on the Wacoma?
That's correct.
Can you tell me what OBS stands for and what they're used for?
So it stands for Ocean Bottom Seismometer, and they are designed to record earthquakes on the seafloor.
The original plan called for us to take out 20 OBSs with cages. Because the style of seismometer and trawl-resistant cage is brand new, there were some issues with the manufacturing process, and until just a few days before leaving port, we thought we would only get 10 or so for the journey.
I think maybe if we can take these piles here, kind of consolidate here, if we maybe get a couple of these rigs. I don't know who's all rigged.
Well, we ended up getting 16 in all, quite a few of them at the last minute, and those not completely finished. We spent all day Saturday on the dock putting the ocean bottom seismometer cages together, painting them with special paint to keep ocean creatures from growing on them during their year underwater.
We're painting these to protect them from the ocean. After our safety meeting, we headed out to sea for our first deployment site.
Going on both the bottom and the top.
Off port side, gents, close.
They're not down there?
We left port on a foggy Sunday morning.
Yeah, it was kind of creepy. Deployment was kind of a test run. We lowered down the OBS with its cage, picked it up twice, then left it on the bottom by lowering it down a third time. Each time we brought it up, we addressed technical issues and made minor adjustments. It turns out science in the field ends up being a lot of make it up as you go. This particular kind of setup had never actually been tried before. It was a prototype specifically designed for a mission that had never been attempted in the past.
I'm Ann Trahue, and I'm a professor at Oregon State University, and I've been out on this cruise as a co-chief scientist.
My name is Maya Tolstoy, and I'm a marine geophysicist at Lamont Doherty Earth Observatory of Columbia University, where I'm an associate professor.
So, we ran into a couple of snags out here over the course of the last week. How did that affect the project as a whole?
The snags weren't completely unexpected because these instruments that we're deploying were being, as you saw, they're being constructed as we were steaming, so it operated on a somewhat faster timetable than we're usually equipped to work on in terms of development of the instruments and building of them. And these